I want to talk a little bit about adhesion measurements and how to determine adhesion forces by the means of in-situ optical analysis in a low-fidelity environment. And first of all, I want to give a little bit of background and motivation behind this work. The work was performed at the Institute of Space System at the University of Stuttgart. It's one of the largest institutes in Europe. And since 2016, we developed the Nanocode microrover. It's a lunar microrover with a tether, and we developed it with in cooperation with von Höhnert and Sölgert. And we are in a state that we have a bedrock model and test the rover within a specific test environment. And the rover is developed for a long-term operation on the lunar surface. As you all know, during the Apollo missions, even a 3-day mission, they had a lot of problem with lunar dust effects, and also the radiation performance degraded a lot. So the lunar dust effects and lunar dust contamination will be a major driver for further lunar robotics and crewed missions in the future. Lunar regolith is a very, very small powder with a checked geometry and is charged and has a high surface energy. So it sticks to everything and is very abrasive. So you have to take care that you don't come in contact with too much regoliths, and to lower the adhesion forces between your surfaces and lunar particles to don't have the effect so much and to be able to remove it more easily. If you look at the forces which are applied to the particles, they are mostly the van der Waals forces and the electrostatic forces, which are dominant in the sizes of the regolith particles. The adhesion forces measured in this work where the measurements are performed with the centripetal force method. So if you apply a force to an individual particle and you exceed the adhesion force, it will move. So we apply a force by the rotating and sample surface. And if now the centripetal force and the gravity combined will exceed the adhesion force of the particle, it will spin off the surface. So we will spin the surface to different rotational speeds and monitor the particles with a microscope in situ in a low-fidelity environment. Our low-fidelity environment, you can see on the left right side. It's a closed chamber where we control and monitor the temperature, humidity, and pressure. So the most important environmental aspects in a low-fidelity environment. And we did our whole experiments in accordance with the NASA standard 1008. It's the standard for testing in planetary dusty environments. This mainly reflected on the selection of the simulant. We used an Exolite simulant, the LMS1 simulant, the regolith preparation, so the breakout process that the water content does not affect the result. And also we follow the testing best practices of the standard. The whole setup has advantages in comparison to a high-fidelity test bench that is very time efficient to test the surface particle interaction, and you can get a large data set of the adhesion forces and the impact of different environmental conditions on the adhesion forces in a short amount of time, which would not be possible with a high-fidelity test stand, where you have the long pump down times for every test series. We detect the particles on the surface with some self-developed algorithms, which uses two pictures. On the left side, you see a sample surface without any particles on it as reference, and on the right side with particles on it. In the first step, we subtract them from each other to remove the background and intensify and fill out the gaps to count them afterwards. As you see, the particles are very small and it's very difficult to identify each particle. So the reference picture has to be really close to the real picture in the positioning. Here you can see in one sample picture from the results. On the left, every particle is colored in a different color. And on the right, if you count them, you see the histogram. I want to now show you an example of the test areas. Here we used an aluminum surface, polished it with 5000 grain sandpaper, and then we spun it up by 500 RPM steps. And you can see that at the beginning, there are a lot of, a little bit more here, but there are a lot of large-sized particles, around 70 to 80 micrometers, and at the end, there are only like 10 to 20 micrometer particles on the surface. You can now assign each particle an applied g-force and its diameter and plot it in this graph here on the right. And now you can see which particle sustained a specific g-force. And as a result, you can approximate a specific adhesion force. Here, the g-force particle diameter relation is illustrated with the black line. And you can see that with higher g-forces, we count more particles. This is because at the beginning, there are particle clumps where particles stick together, which fall apart at higher RPMs, where our accuracy also increases because we can more easily detect the individual particles. With this black line, we can now calculate the adhesion forces. And as you see here on the right, we plotted the theoretical calculated values and the measured values. The green most upper line is a calculated value for a smooth surface, and the light blue one for a rough surface. So you can see the measured results match with the rough calculated surface. So you obviously have to consider the roughness, and the method we developed worked into measuring the adhesion forces. So in conclusion, the results match our calculated values, and we have a repeatability within one order of magnitude. But we learned that you really have to take care about the deposition method of the regulator to avoid particle clumps. And that is really difficult to detect these particle clumps because the brightness difference between each particle isn't a lot. And in the future, we want to improve the camera resolution to be able to better detect these particle clumps, and a position improvement to improve the reference picture. And for promising surfaces, we will do the high-fidelity testing to accurately determine the adhesion force in a high-fidelity environment. So thank you for your attention.